Today, I want to go and talk about SIMS data analysis. I really want to go back to some of the basics of things that I wish I had known when I first started SIMS. I'm not going to go into details about multivariate analysis today. I'm just going to stick to some of the fundamentals. And let's see. So I recently published a couple tutorials that are in biointerfaces. This is part of a tutorial series that biointerfaces is doing on ToF-SIMS analysis. So there's two that are published now. There's a couple others by other authors that are in progress and should be released soon. And the hope here is to really get some basic tutorial information about how to set up ToF-SIMS experiments, how to analyze the data, and how to work with different types of samples like tissues and bones and polymers and things. So I'm not going to spend a lot of time talking about how SIMS works today. I'm sure that will be covered in this seminar series multiple times, but the basic concept is we have a primary ion gun that shoots ions down onto a surface where there's an impact, an explosion, and material is released, some of which is ionized, and those ionized species are then extracted and detected into a detection system. This is a little bit more detailed schematic of a SIMS instrument. It's all under computer control. There's transfer arms because we have to be able to bring the samples in from atmospheric pressure to ultra high vacuum pressures. And then there's typically some sort of charge neutralization system that we need in order to neutralize because we're removing charges from the surface. So most time-of-flight SIMS systems operate using a time-of-flight detector. And the concept here is that the ions are extracted into the detector and set to a constant energy. And since they're all accelerated to the same energy, they'll separate by mass, with smaller ions traveling faster than larger ions. And so you can determine the mass from this equation. The computer does this for you while you're analyzing your data to be able to determine the mass to charge ratio of the ions. In time-of-flight SIMS, the charge is almost always 1, and so you can pretty much interpret the mass scale just as a simple math. Luckily, Hollywood gave us a demonstration of how the SIMS. And so here we see impinging ions coming into a surface, causing an explosion. There's emissions in the SIMS process. Some of these would be ionized. And then once these ions are extracted into the detector, we can then look at the different parts that came off and try to extract where those ions came from. So for example, these ions came from the Chrysler building, and these ions here came from Yellow Cat. The SIMS process is very similar. We're getting fragments, in this case, of molecules that are on the surface, and then we look at the fragments we get in the spectra and try to relate that back to the original molecule that was present before the impact. And so it really is kind of like solving a puzzle. So in this collision cascade of ions that come into the surface, there's a transfer of energy causing disruption in the near surface region, and the emission of atomic species, fragments of molecules, and in some regions, intact molecules. And the fragmentation process can be slightly different if you're using monatomic ions or polyatomic ions, but I don't have time to discuss that today. But it's a surface mass spectrum that we're getting. In most cases, we're looking at the upper 1 to 2 nanometers of the surface. And in many cases, we operate instruments in a so-called static regime where the dose of ions is less than 10 to the 13th. Though it has become more common recently to actually exceed this limit with some of the polyatomic ion sources that have been found to generate large yields of molecular species, particularly from organic and biological samples. I kind of discussed this a little bit in the previous slide, but the generation of ions, typically we get most of the atomic species from the point of impact, and as you move away from that point of impact, you start to get fragmentation and then emission of molecular ions, and then you reach a point where there's no emission because the energy propagation is stopped throughout the surface. So in that process, we generate a large amount of material. However, over 99% of what is sputtered is typically neutral. And so we don't actually analyze that unless you use some sort of post-ionization. There's also so-called matrix and primary ion source effects that can affect the ion yield for different surfaces. But we, regardless of the primary ion used, we end up with both positive and negative primary ions. And in most systems, you have to analyze those separately. So you have to collect your positive ion data and then your negative ion data. But there are some general trends of where peaks will show up in a spectrum. For example, metal ions tend to show up mainly in the positive ion data. Your halides tend to show up predominantly in the negative ion data. Salts tend to show up in the positive ion data. And then there's some general trends where your oxides and oxygen containing peaks are typically more prominent in the negative ion data. However, they can show up in both. And one of the take-home messages from this is that you really need to collect both positive and negative ion data to fully characterize the surface using SIMS. It can be possible that you'll find one polarity has more peaks that answer the question that you're looking for, but to really understand the chemistry of a surface, you need to collect both positive and negative ion data. So one of the reasons people use SIMS is it has a very good detection sensitivity. People report being able to detect things in the part per million or part per billion range. It has, I used to say SIMS has high mass resolution, but that really depends on the analyzer you have on your system. I usually call it good mass resolution now because in most cases, you're looking at a mass resolution of maybe 6 to 10,000, which in today's world in mass spec, that's actually quite low since many instruments now can get mass resolutions in the 100,000 or a million range. However, there are some newer SIM systems. Can you mute your microphone, please? Thank you. And even though the mass resolution is decently good, we still get the ability to determine the exact mass of molecules. We get isotopes. And we also can do chemical identification. As I mentioned before, we get both atomic, molecular, and fragment species. It is interesting, if you look in some of the literature, some people claim that the high fragmentation in SIMS is a disadvantage, but I would argue that the fragmentation we see in SIMS is actually an advantage because there are many things that we can determine from the fragments that are present in the spectra. And we're also looking at the near surface region, so we can tell surface modifications and things that are happening in that region. And with modern instrumentation, we also have the ability to depth profile, and we have very good imaging resolution that can even be sub 0.1 micron resolution, depending on your instrument and the gun that you're using. So I'm not going to read this whole slide to you, but there's a wide range of things that we can analyze, and basically anything that you can stick into an ultra high vacuum environment, and even some things that typically can't go in ultra high vacuum environments can be analyzed if we freeze the samples or do some other special treatments. But you can see there's pretty much a list of almost anything you can think of that people have analyzed with SIMS. And this ranges anywhere from polymer materials to organic cells and tissues to things like dirt and even worms and other little critters. So before we get into talking about how to process the data, I want to talk just briefly about how you get ready for an experiment, because it really is important to know what you're going to analyze and to have as much information as possible about the sample in order to interpret your data. And so I always recommend that SIMS is not really the best method to start with when you're starting an analysis, that it's best if you can have data from other methods that give you information about either the composition, for example, from XPS, or maybe even some information, some imaging information from other methods like AFM that give you some topography information. And if you're looking at something that's a multi-component system, it's often useful to analyze controls of the components that you know might be present, so that you can determine what are the main peaks that you could be looking for. And I always tell people that the first experiment you do with the SIMS rarely works as planned. Usually you find out things about surface contamination and sample preparation that you need to fix. And so it's always good to start simple and then work out any issues and then increase the complexity of what you're looking at as you go through your experiment. It's also, since SIMS is surface sensitive, we do see contaminants. It's also, since it has high sensitivity, we can detect ions very easily. And many of the things that show up as contaminants actually have very high yields in SIMS experiments, such as your salt ions, that even when they're present in very small amounts can have a very intense signal. And the salt ions are important also because they can also affect the yield of other species within the spectra. Hydrocarbons are basically any surface that you expose to air is going to have some hydrocarbons, and that could be just from the air. It could be from if you mishandled your samples. And then one of the main ones that you almost always see is the silicones, predominantly PDMS, that can come from pretty much anywhere. And it's actually, PDMS is pretty crazy, because if anyone just opens a container of PDMS in your lab, you can assume that your entire lab is contaminated. And we often get people who are surprised because they're like, I don't use PDMS. And then they have PDMS on their sample, and then they find out that someone else was doing PDMS in an adjoining bay in their lab. So to avoid contaminants, it's important to use silicone-free gloves. There are some gloves that actually use silicones as release agents. We found that polyethylene and most purple nitrile gloves tend to be clean and okay. But even with your gloves, you should never touch your samples directly. You should always handle them using tweezers and tools. And we always clean off all our tools with acetone and methanol before and after handling the samples. And just in general, try to avoid silicones in our lab and in the sample prep areas. And PDMS, once you have it, it can be removed with hot soapy water or hexane. Other solvents really won't touch it. But obviously these cleaning methods aren't great for most sample types, so it's best just to avoid it. Okay, so now we've prepared some samples and we've got some data. So what do we end up looking at? Well, we can look at the SIMS data as an image. We can dice that image into pixels or groups of pixels and generate spectra. And we can also sum all the spectra from all the pixels and get a so-called total ion spectrum. Or we can also integrate the areas from individual peaks within the total ion spectrum and generate individual ion images that show us the distribution of where those ions are located across our surface. We also have to think about how much data that we need. And this would depend partially on the type of study you're doing, but in general, if you have samples that are reproducible and homogeneous, we always recommend to take 3 to 5 spots across 2 samples. And if you have something that's less homogeneous, we recommend taking 3 to 5 spots across 4 to 5 samples. And it's best if your replicates that you make are made on separate days. And this is so that you can test both the repeatability and reproducibility of your sample surface. But in general, you need sufficient data to be able to tell if you have statistical significance of the differences on your surface. And this is particularly important if you plan to use multivariate analysis methods, because multivariate analysis methods are all designed to look at variance in the data predominantly, and it will find differences between whatever you look at. So if you only collect 1 or 2 spectra per sample, it's highly likely you'll find some sort of difference, particularly if those samples have some variability. Just as a quick example, this is some data from self-assembled monolayers on gold. This is showing 3 spots per sample on 2 different samples. So there's 6 data points per sample type. And here we're looking at a scores plot where the y-axis is the principal component analysis scores, and the x-axis is the chain length. And you can see on the scores axis, most of these spots from each sample overlap quite nicely, showing that these spectra are mostly reproducible, and we get a very tight grouping. If we contrast that with some data taken from a study from Matt Wagner, where he looked at proteins absorbed onto mica, and this is actually just a subset of the data that he collected. And if we looked at just the subset, it looks like things do group fairly tightly for each of the proteins. This is now a principal component analysis cross plot of principal component 1 on the x-axis and principal component 2 on the y-axis. So we're looking at groupings on this principal component analysis plot. But if we look at all the data that he collected, we can see there's quite a bit of variability in some of these proteins in their absorption onto mica. Though in most cases, we can still separate them out. You can see they cluster together on this plot, showing that they have spectral differences. But I think this is a good demonstration that shows that you really need to sometimes collect a large amount of data to be able to get statistical significance in the separation you see within your samples. So once you have your data, before you start doing any peak analysis, you need to make sure that it's calibrated. In some cases, you can calibrate while you're collecting the data, but you can always calibrate the data after. And it's always good to recheck your calibration to make sure that, because sometimes if you're not calibrating every spectra while you're collecting it, depending on what system you're operating on, you can have some drifts in the calibration. And the calibration consists of identifying known peaks and telling the software where they are, and then the software interpolates the mass scale to line up the masses in the correct area or correct place. There's always going to be an error in this calibration, and the error will get higher as you go to higher masses. So, it's in adding a higher mass peak. I'll talk about this a little bit more in a subsequent slide, but if you can add higher mass peaks, it improves the calibration on the high mass end of your spectrum. But whenever you're doing an experiment, it's recommended that you calibrate the data on the same set of peaks for a given experiment so that you have a consistent calibration. And the most important thing in calibration is you must know the identity of any peaks that you're calibrating on, because if you calibrate on something and you're just guessing and you're wrong, then your entire mass calibration will be wrong, meaning all the identities of your peaks will likely be wrong. So we always recommend that you calibrate your data by on the centroids of the peaks. And so the way we define a centroid is the location of highest intensity of a given peak. And it's important to note that because there's some software that will put the centroid of the peak at the center of mass. So if you have a peak with a shoulder, which often happens in ToF-SIMS spectra, the centroid position will be shifted towards the side of that shoulder. And the result of that is if you use that centroid, then all the centroids of all the peaks will be shifted. So if you are trying to identify a peak based off the location of highest intensity, your location will be wrong. So in some software, you can actually force it to use the location of highest intensity in your calibration. And I always highly recommend that because it puts the centroid of the peak in the correct location. For calibration, you need at least 3 peaks. including more peaks can be helpful, but there's kind of as you go to more and more peaks, the changes you see in the calibration become less and less. As I mentioned before, if you can include a high mass peak, it will improve your calibration, but you once again have to know what that peak is, and that can become increasingly difficult as you get to higher and higher masses. If possible, I always recommend calibrating only on symmetrical peaks to avoid the issue I talked about in the previous slide. However, if all your peaks are asymmetrical because of either charging or something else, then you don't really have a choice. So as I mentioned before, trying to do the calibration on the centroid location at point of highest intensity is recommended. And in general, you should be able to get your calibration errors below 20 part per million. Depending on your data, that could be more difficult. If you have a very rough sample that charges, your peak widths are going to be wider, and so your errors might be higher. But minimizing that will help in identifying your peaks later on. This is just a quick example showing a bunch of spectra that are overlaid. And you can see that it looks like there's actually two groupings of peaks here. And if this data was calibrated correctly, you would actually think there was two peaks located here. But after checking the calibration to make sure everything was consistent across the data set, you can see they mostly overlap in one central location. And so it's always important to go back and check the calibration before you start your analysis. So just to demonstrate or give an example of how adding higher peaks can improve your mass calibration, if we look at stearic acid, so this is a fatty acid, has a molecular ion located at 283 mass units. And if we calibrate just on a default set of CH, C2H, and C4H in the negative ion data, we see that this molecular ion appears at this mass with an error of 57 ppm. If we then add a slightly higher mass ion to the calibration set, it reduces the molecular ion centroid error to 36 ppm. And then if we use a subfragment of stearic acid, the C12H21O2, to the calibration set instead of the C3H3O2, it reduces the error in the molecular ion centroid down to 18 part per million. And so in the case of this, because stearic acid fragments in a very an easily determined way, and subfragments cutting this chain apart, it's easy to find higher mass ion that were the identification calibration for these higher mass peaks. So what kind of things do we have that interpret our peaks and understand what they are? Well, we have our good high mass resolution, so we can separate out individual peak isotopic patterns, which can become very helpful in identifying peaks that are. You can also isolate samples if you are trying to identify a specific type of peak, and analyzing standards. So I mentioned before, for multi-component systems, if you know what is supposed to be on the surface, you can analyze standards of each of those and do derivatization to try to functionalize groups to help identify. And then some SIMS instruments have the ability to do tandem SIMS, so MS-MS experiments where you can fragment an ion to determine the daughter ions to help you reconstruct what those molecules are. And then there's the literature and handbooks and things that we can reference from. So we have a whole bunch of different tools that we can use. We can also, the more you look at SIM spectra, the more you'll start recognizing typical patterns. So in the 0 to 50 range of pretty much any spectrum, it's very typical you'll see a pattern similar to this. Sodium and potassium are common ions that show up on lots of surfaces. And then we have just fragments that will come from either hydrocarbons absorbed to your sample or molecules that are present in your sample that contain carbon that will give you a cluster of C1, C2, and C3 atoms. And the relative intensity ratios of these peaks typically look like this. There are some exceptions. However, for example, at the C2 cluster, you typically see C2H2 is small, C2H3 is bigger, C2H4 is small, C2H5 is bigger. And because of this repeatable pattern that shows up in the SIMS spectra, you can get a set of default calibration peaks to start your calibration in case you really aren't sure what's present on your surface. And in the negative ion data, we have a similar set of pattern low mass peaks that tend to show up on all spectra. And so in a way, the absorbed hydrocarbons on your sample actually help you because they give you a place where you can start your initial calibration. SIMS spectra, we've all looked at them. We can see there's peaks across basically the entire mass range. If we zoom in, you see that there's peaks at every mass, and in some cases there's more than one peak at each mass. And then we have this good mass resolution so we can determine the centroid and help us identify what peaks are present on the surface. There's also some little rules of thumb you can use where if we call unit mass a whole number mass, if we look at peaks that are above unit mass, they tend to be organic. If we look at peaks that are below unit mass, they tend to be inorganic. So in this example, we see there's two peaks above unit mass here, which are CH2N and C2H4, both organic species. And we have a peak below unit mass here at 0.9759, which comes from silicon. And so this is a quick little way you can scan through your spectra and just kind of look at what's above and what's below. And this can help you identify what things you might be looking at. There's obviously some exceptions to this, but this happens because the organic elements, carbon, hydrogen, and nitrogen, all have masses above a whole number mass, and most inorganic species have masses that are below this whole number mass. Oxygen is kind of an exception, but when you add oxygen to a bunch of carbon and hydrogen, the masses tend to be above unit mass. We also have isotopic resolution, so we will see the isotopic distributions of different elements, and some of these are quite characteristic. So when you see like a doublet of similar intensity, it's likely that you have either bromine or silver. Chlorine has this kind of 3-to-1 intensity of isotopes that shows up repeatedly. And then silicon and sulfur also have some unique isotopes. And if you're dealing with inorganic elements, there's some very characteristic isotopes. We'll look at some of those in a moment. So how can these isotopes help you? Well, if we take this peak here, we see the main peak, and in most mass spec literature, they call the main isotope A, and then the next isotope A+1, and so forth. So if we look at this isotopic pattern, we can determine the ratio of these isotopes to the main isotope and get a percentage for our unknown species. We know the exact mass, and then we can use a formula finder. So basically type this mass in and ask for what combinations of elements can match that given mass. And here I list a bunch of combinations that matched within a given tolerance to this centroid mass with their mass deviations. And then we can look at the isotopic percentages for the peaks that it suggested in the formula finder. And we can see that there's two that match quite closely. If we look at the actual isotopic patterns plotted out and compare it to our original molecule, we can see that something like what's shown in B definitely isn't the correct identity because the isotopic pattern isn't anywhere close. And then these two here that we identified from the table before have very similar patterns, very similar peak intensities. And it turns out that in this case, this is a alkane thiol molecule on gold, and the correct identity is this gold thiol cluster that's very typical from self-assembled monolayers. So we can use the isotopes to eliminate potential matches and help us isolate down to what a good match would be. As I mentioned, some of the inorganic species have very unique isotopic patterns. I've done some work recently with perovskite materials that have chlorine, bromine, iodine, lead, and cesium. And these spectra can be very complicated because you get combinations of all these different ions, but they have very unique isotopic patterns in some cases. And so, for example, when you see something like this, you can, using isotopic calculators and the exact mass of the peak, you can determine that this is a PV2 peak, which is the summation of the isotopic pattern from the two lead ions. And then something like this, we can see we have the superposition of the lead isotopic pattern with the bromine isotopic pattern that gives us this unique pattern. So whenever you see a pattern like this in the spectra, you know that you have lead and bromine. You can also have some cesium and iodine because they're monoisotopic. However, it does help you minimize down to the possibilities that can match these types of patterns. And this is just another snapshot from a spectrum from a perovskite material. So we see a pattern here that looks very similar to lead, a pattern here that looks very similar to bromine, and then a single peak. So this could be iodine or something that contains iodine or cesium. And then it turns out this is PBI, CS2BR, and CS2I. So you can use these patterns to help you identify what things that you're looking for. You can also look for just patterns within the spectra. So this is a spectrum from the mass 500 to 1200 of a polyethylene glycol polymer. And you can see this repeated loss pattern of the monomer group, the C2H4O. And so whenever you see this kind of repeated loss pattern across the spectrum, you can determine what that loss is, which can help you determine what the structure of your molecule is. And in this case, we actually have two overlapping patterns. We have this kind of Gaussian curve showing the molecular weight distribution of the intact polymer chains. And then the secondary pattern here of fragmentation of those chains, showing the loss of these monomer units. So we've got patterns we can look at, we've got isotopes we can look at. So how else do you approach this spectra? So I always recommend you look for what you expect to see. So if you're analyzing something and you think that you may have had something there, or from the literature you found some things to look for, I always recommend to see if that's there. I usually focus on the most intense peaks first because they do tend to be the most prominent, though because of the ionization differences between peaks, they may not be the ones that are present in the highest amounts. And then there's also the spectral libraries. If you do use spectral libraries, or you have a paper or previous research that you know a set of characteristic peaks, it's important that you are able to find the majority of those peaks to be able to make a match. If you only see 2 out of 10 characteristics peaks, it's unlikely that you have a match. And when you're matching masses to expected structures, we always recommend that the match should be within 50 parts per million, which for most SIMS instruments will give you a good rule of thumb of what would be an exact match to a given peak. And I always tell people to be skeptical when you're analyzing your SIMS data. Just don't believe what a mass calculator or the software tells you. You really need to understand whether the matches you're making are correct. I'm not going to read this whole slide, but these are some common peaks that show up in SIMS spectra. So common PDMS peaks, salts, if you're looking at like alkane thiols, there's a whole series of peaks that show up. Metal oxides, even if you have a quote oxide-free sample, you'll often see metal oxide species. And typically the intensity of these peaks will follow trends you would expect based on the ionic structure and the types of oxides that these peaks will form. But these are typical peaks you can look for if you have these types of materials in your sample that you're looking at. So I mentioned spectral libraries. These can be good for identifying some standard materials and fingerprinting and identifying some unknown compounds. But the bad thing is about spectral libraries and standards is they're usually always based on pure compounds, but most things aren't pure. And then you can also find that characteristic peaks can overlap from different compounds. So this can become problematic. For example, I did a study once looking at a mixture of lipids with protein, trying to determine if we could detect the protein within the lipids. But it turned out that since we were using a lipid that had a nitrogen in its head group, it could form fragments that were identical to most of the protein peaks that we would look for. And so that limited the ability to separate out those two materials. And then it's also important to remember that the libraries are limited to whatever's in the database. So they don't contain everything. So I always ask myself, does this make sense? For example, if you use a low mass peak like 27.023, the two best possible matches are C2H3 with a part per million error of 14.8 or BeH2O, which is even lower at 11.1. However, in most cases, I've never analyzed anything that had beryllium on it, so it's not logical to assume that we have a beryllium compound, even though it has the lowest part per million error. It's also good to know the limitations of the tools you're using to identify your peaks. Is it a database? Are they using a formula calculator? What are the constraints that they use or you can use? And then if you're using your instrument software that contains a peak ID function, know how they're doing it. For example, the IonTOF software uses a peak database, and that peak database is fairly extensive, but it does not contain everything that you could potentially analyze. One tool I like using a lot is the molecular weight calculator by Matthew Monroe. It has a molecular weight calculator where you can type in a formula, make sure you have it set on isotopic masses. You type in a formula and it will give you the exact mass. So you can use that to basically figure out where to look for certain peaks. It also has a formula finder where you can put in a target mass and an error, and you can even type in what types of elements you think would be present and give a range of how many of those elements. And then you can calculate, basically it calculates matches based on combining atoms that match that mass. And it is important to know that that's what it's doing, because it can make matches that are complete chemical nonsense. So for example, if you look here, it came up with a C17H186O3S5. So I don't know how you would even get that many hydrogen into something with only 17 carbons, but it did match very well with the given mass, but it's literally just taking all the atoms together and combining them. So it's important to know what the calculator is doing when you're trying to determine matches. And then his program also has a isotopic distribution calculator, which gives you the percentages of the isotopes and also a nice little plot showing what the isotopes look like. And this could be very useful when comparing isotopic patterns that you see within your spectra. So we've talked a little bit about identifying peaks and seeing what's there. So how do we display this data once we've got it? So we can display the data as our spectra. We can do peak areas in line or bar charts. We can do images in 2D and 3D. And I just want to go over some tips on some good ways to think about how to display your data. And what you choose to display will be determined by what you're trying to tell in your report or your presentation. So in some cases, images are going to be important. In some cases, it may be the spectra. It depends on what the story is that you're trying to tell. But whenever you're reporting on data, it's important that your data should be normalized to remove variations that could be caused by the instrument. Whenever you do any kind of data processing, you're making an assumption about the data. And so when you normalize your data, you're assuming that that parameter that you're normalizing by doesn't describe any differences within the data, because when you do the normalization, you're removing that from your data set. Some common normalizations are normalizing to the total counts or to the sum of a set of selected peaks or to a specific peak. And the way you normalize will be determined by what you're trying to demonstrate in that data. Displaying spectra, I have mixed feelings about displaying spectra, particularly in papers. If you're reporting on a new material, then displaying the spectra for that, I think, could be very useful. If you're reporting on a known material and just some trend that you're finding, I don't find a picture of the spectra to be that useful. But if you do display spectra, particularly for multiple samples or multiple spots, it's important to normalize the spectra before you display them. And spectral overlays can often be useful in showing sample differences. So I do think spectral overlays can be helpful. When you display your spectra, you should label your axes with your counts or normalized counts, your mass, and then only label major peaks to maintain clarity in the spectra. I show this spectra because this is a good one to recognize. This is actually a sample contaminated with PDMS, and we see the characteristic peaks in their relative intensities that you'll see in the positive ion data from PDMS. If you want to show a specific peak, you can do a blow up that shows either the peak shape or some smaller peak that you're looking at. In this case, I highlighted this to show this is the SIC3H9 from PDMS, and it has this typical high mass shoulder. And all the PDMS peaks in the positive ion data have this type of shoulder on them. So if you see these masses and you see this shoulder, then you know you have PDMS on your sample. Spectral overlay can be useful to show differences in relative intensities of peaks, but you need to make sure you normalize them before you display them. And then it's also useful to use different colors for, these are 3 different samples that had 3 different levels of PDMS on them. And you can see a clear separation. Though I would note, I actually chose a really poor set of colors because there's lots of people that are red-green or blue-red colorblind. So we need to think about colors too. When we're integrating peaks to get peak areas, it's important to set those integration limits consistently. We recommend to set the limits just below the full width at half max, and that makes it so that you can have consistent peak limits even when you have overlapping peaks. So you're not oversampling a signal that could be from adjacent peaks. If we're going to do a peak area plot, a simple way to do that is a bar chart, where in this case, the bar is showing the average, the error bar is showing the standard deviation. And then from this type of plot, we can look at the relative intensity of these. And though SIMS is not quantitative, we can get an idea of the relative differences between these samples and see that there's, for this peak, there's twice as much in sample A as there is in sample B. So these qualitative differences are real and informative, but we do need to make sure that our data is properly pre-processed. So when displaying images, we should use a logical color scheme. A typical one people use in MATLAB, it's called HOT, but it's basically a black to white gradient that goes through colors of red, orange, red, and white, or yellow and white. And grayscale is useful to avoid issues with colorblind people. There's this website here, vischeck.com, that can be used to check your color scheme to see if people would have a problem seeing it if they are colorblind. It's important to show your scale bar and also to give any details of the image processing that you've done when you report on that data, because people need to know, did you adjust the brightness and contrast? Did you normalize? What did you do with that? And then when comparing images for the same peaks from different samples, it's useful to make sure that the color scales are the same across all the images, so you're comparing against a common scale bar. These are just some different, or same image with different color schemes that I see a lot in the literature. So hot, gray, or jet. I do think the gray scale is actually a good choice in many cases to avoid issues with color, as I mentioned before. What I was mentioning about matching color bars, this is a sample of an ion from a treated sample. So in this sample, this ion is quite intense across the sample. And in the untreated sample, we see just basically background noise. But here we see the maximum counts in this image is 15. The maximum counts here is 4. If we rescale now this bottom image so it has matching color scale, you can really see the contrast between these two. And it is important to note there are some background noise signal in this sample, but with the scale bar not being adjusted, you may think that this intensity is actually higher or more important than it actually is. I didn't have a chance to talk about multivariate analysis, but it's also important to think about your color scale when plotting principal component analysis scores, since you have both positive and negative values in principal components analysis. So if you use any of these top 3 scales, your 0 will be some shade of gray or orange or green. But if you use a scale where 0 is black and then a color is red, or color red is positive, green is negative, for example, you can get very good contrast between what's positive and negative in your score values. So if we then want to do something in 3D, it's really important to think about what you're going to show, because the way software displays 3D data, you can show pretty much anything you want. You can choose between an isosurface, which is basically a surface plot of equal value locations within a data set. You can do a volumetric rate rendering that creates a 3D version of your data by displaying basically pixels as voxels. And then, as before, you need to state whether you did any scaling or adjusting before displaying your images. But really, you need to understand what the software is displaying, because most 3D methods interpolate 2D pixels into 3D voxels. And the z-axis, when you display 3D data, is pretty much almost never to scale. And if you don't do any type of z correction or correct the z-axis, your data will be forced into a cube, basically. There's a couple different options. If you look into z correction, there's some papers out about this, but it's also included in the ToF software, and then my software, the NB Toolbox, has a z correction routine to do that. But as before, it's important to report what you're displaying. This is a simple volumetric render from the ToF software of iodine, silicon on the bottom, and then this organic additive. This is from a perovskite sample. You can see the data has been forced into a cube. We can see a green layer of this organic molecule at the top, and then the iodine in the middle. So it does give us an idea of relative positions of ions. If we compare this volumetric render here and here, this is just a volumetric render of the peak at mass 101. If we compare that to an isosurface render, all 4 of these pictures at the bottom here are the same data for mass 101, but using a different setting for an isosurface. And so the isosurface basically is, you're telling it to display a different portion of the data and that meets a criteria that you select. So when displaying an isosurface, you need to be very explicit about why you chose a given setting, because you can basically display whatever you want from that data. And so it'd be very easy to force it into what you want to display and not really what the data is showing. It's also, you can do things with transparency. So this is a 3D RGB overlay of 3 mixed polymers. And in the top image here, I lowered the transparency value of the green. And you can see it looks completely different that if I lower the transparency value of the green channel. And since you can choose the properties for all of these, you can basically show whatever you want, but it's important to state why you chose a certain level. For example, if I really wanted to show the distribution of these other two polymers underneath the polymer shown in green, I could report that I lowered transparent or increased the transparency value to show what the data looks like underneath that top layer. But it's important to make sure you state why you did something, because it's very easy to manipulate 3D data. I'm not going to read this slide. This is all contained in one of the tutorial papers I noted previously, but this basically has a list of things that you should report when you're reporting your ToF-SIMS data. But basically, you need to report anything that needs to be known to be able to reproduce the data that you created, so someone can repeat your experiment. And so that includes your settings for the instrument, the guns, charge neutralization. It is important also to state whether you had saturated peaks in your spectra. I did not cover saturation, but in some instruments, the ion guns are so efficient that they can actually produce more ions than the detector can handle, and so you can saturate your detector. And peak saturation, you should never do any semi-quantitative analysis or principal components analysis with peaks that are saturated, because the answer will be wrong. But it's important to note whether you saw saturated peaks and the other details people would need about how you processed your data and how you displayed any of your images in the spectra. So with that, I would be happy to answer any questions that you have, and thank you for your attention.